There is a realm beyond that known to most technicians. It lies between the summit of their potential and the reality of their current ability. A place that might be called the Tech Zone. The case of one George Smith, a knowledgeable motorcycle technician whose understanding of two-stroke technology is about to come on the pipe.
Thanks, Wendy. Hey, Wendy. I'll trade you these 3 two-stroke repairs for just 1 4-stroke.
No deal. Those jobs are promised before the weekend.
George has just received 3 two-stroke repair orders and a round-trip ticket to Honda's Tech Zone.
Hey, what's going on? Who are you?
I'm TechMan, and this is Honda's Tech Zone. And you're about to learn as much about two-stroke engines as you already know about four-stroke engines.
Great, but where?
George, if you take a look at the screen, it'll show you exactly what you're going to learn. First, you'll be able to explain Honda two-stroke engine operation. Then you'll learn how to troubleshoot and maintain Honda two-stroke engines. And finally, you'll be able to calculate two-stroke carburetor jetting for changes in altitude and air temperature. Now, let's take a look at a cutaway Honda two-stroke engine to see what makes it work. We'll begin the two-stroke cycle on the upstroke of the piston, when a vacuum is created in the crankcase and intake port. As this happens, the reed valves open, allowing the fuel mixture to fill the crankcase. Just before the piston reaches top dead center, the spark plug fires, igniting the fuel mixture, forcing the piston down. The piston pressurizes the crankcase, closing the reed valves and compressing the fuel mixture. As the piston continues its downward stroke, the exhaust and transfer ports are uncovered. The pressurized fuel mixture in the crankcase enters the combustion chamber through the transfer ports, forcing the spent gases out the exhaust port. Then the piston begins its trip upward again, forcing the remainder of the exhaust gases out, closing off the transfer and exhaust ports, and finally compressing the fuel mixture before the spark plug fires.
So all that happens in 2 strokes of the piston. You know, that crankshaft and connecting rod looks different than a 4-stroke.
A two-stroke crankshaft is different from your typical four-stroke crank. Because fuel mixture is pumped in and out of the crankcase, there has to be a positive seal on each end of the crankshaft. Honda uses a gasket to seal the halves of the crankcase together, and the crankcase is physically separated from the transmission. The crankshaft assembly is pressed together, and the one-piece rod has cage needle bearings at the big and small ends. This slot, and the side clearance between the big end of the rod and the crank halves, allows oil in the fuel mixture to lubricate the rod's big end bearing. And the small end bearing gets lubricated through this hole in the small end, as well as through side clearance. Now, let's take a look at another big difference between 2 strokes and 4 strokes. The exhaust system.
Yeah, this pipe is a pretty complicated shape. How come?
The head pipe and diffuser cone use exhaust pulses to create a vacuum in the exhaust port. This not only draws out exhaust gases, but it also helps draw fresh fuel air mixture into the combustion chamber. As the exhaust pulse reaches the baffle cone and outlet pipe, it sends back a reflected sonic wave, which keeps the fresh fuel air mixture from escaping through the still open exhaust port, and the outlet pipe creates just enough back pressure to enhance the reflected sonic wave. This expansion chamber design is most efficient within a fixed RPM range.
Hey, I bet that's where the saying "comes on the pipe" started.
Right, this increased efficiency in the power band is really obvious on some models. The effect is softened by optimizing the port timing, crankcase volume, carburetor, airbox size, or ignition timing. And on some Hondas, the automatic torque amplification chamber, or ATAC for short, simply varies the volume of the head pipe for high efficiency within a wider RPM range. When it comes to port timing, the size and opening duration of the exhaust port is crucial to the power band of any two-stroke engine. Generally speaking, as the piston travels downward, the later the exhaust port opens, the greater the power at low RPM. On the other hand, the earlier an exhaust port opens, the greater the high RPM power. With Honda's power port system, the size and opening duration of the exhaust port is variable for an even higher and broader power band.
Gets complicated.
Not really. It's done by using two exhaust valves controlled by a small governor assembly on the water pump shaft, a rack and pinion, and a series of levers.
Does it require special maintenance?
Ideally, both exhaust valves and their guides should be decarboned every 2.5 hours of engine operation. The service manual does a good job explaining troubleshooting and service procedures, so use it when the time comes. Now, don't you have a scooter that needs repair?
Yeah. Well, according to the RO, the scooter won't go over 20 miles per hour, and the customer mistakenly put 30-weight motor oil in the oil tank, and on top of that, they haven't had it serviced in over 6,000 miles. So first of all, I figured I'd replace the 30-weight motor oil with Honda two-stroke oil. Maybe that'll help.
That's a good start. Honda two-stroke oil is specially formulated to minimize carbon deposits. But you should read this copy of the wrench from September 1984 before you go on your test ride. It may help you to diagnose this scooter's problem.
The wrench says I first test ride a known good scooter using an electronic tachometer and note the engine RPM at certain road speeds, including full acceleration up to the posted speed limit. Then, test ride the scooter in question with the same electronic tachometer connected. Compare the RPM and speed differences between the good scooter and the customer's scooter. If the RPM of the customer's scooter is too high in relation to road speed, the drive unit is probably slipping. If the speed and RPM upper limit is too low, the engine more than likely needs adjustment or repair.
Well, how did it go?
Even after changing the oil, the scooter still won't go over 20 miles per hour. So comparing it to the good running scooter indicates that the engine is the problem.
Take a look at the service manual. That's the best reference for further troubleshooting. But don't forget to check the service bulletins on this model before beginning any work. In this case, you'll need NQ50 number 2, revised in September of 1985.
Scooters with frame numbers below 158715 may run poorly due to carbon deposits in the muffler, exhaust port, and combustion chamber. And that applies to this scooter, so I better put a new muffler on it. Yeah, there could be other problems, though. Well, I've checked the fuel petcock and the air cleaner. What's next?
How about a compression check?
Wow, this compression is really high.
Remember, the service manual says that unusually high compression can be caused by carbon deposits in the combustion chamber or on top of the piston.
I'll remember to check that later, but first, let's check the fuel system. Well, the float level checks out okay. That leaves the auto buy starter. What does it do?
The auto buy starter enriches the fuel mixture when the engine is cold. As the engine warms up, an electrical heating element returns the fuel mixture to normal.
So if the heating element of the auto buy starter were to fail, then the fuel mixture would be too rich after the engine warms up.
Right, and the rich fuel mixture could build carbon deposits in the combustion chamber and exhaust system. Use the service manual to troubleshoot the auto buy starter. Then, if it's working out right, we'll check the ignition timing.
Well, the timing looks right on.
The timing is electronically controlled and is not adjustable. If the timing were out of tolerance, we'd have to check every ignition component as well as the Woodruff key that positions the flywheel. A shared key won't show up during the timing check, but the engine would definitely be out of time.
We haven't found anything else wrong yet, so it looks like carbon in the combustion chamber and the exhaust system is the problem.
You're probably right. You remember the unusually high compression check?
Yeah, it was high, especially for a scooter with over 6,000 miles. I mean, even if the customer put in the right oil, the service manual says that the engine should be decarboned every 2,000 miles.
Yes, and it's important to decarbonize the exhaust port as well as the cylinder head and piston crown. You'll have to remove the cylinder head and cylinder to decarbonize the exhaust port, or risk damaging the piston or dropping carbon into the crankcase.
I'll clean the cylinder head and piston crown first.
When you finish with that, I'll show you how to clean the exhaust port. A 10mm bolt works well to remove hardened carbon from the exhaust port. When removing carbon from the piston, exhaust port, or cylinder head, use care not to gouge the aluminum. Gouges provide a ready surface for carbon deposits to build up. And when you're done, be sure to clean all parts thoroughly. After you assemble the engine, a test ride will verify that you fixed the problem. And when you get back from the test ride, we'll take a look at that TRX 250R.
Removing all that carbon and putting on a new muffler really made the difference. That scooter runs great now. What's next? While riding in the desert, this TRX just slowed down and stopped. Well, they got it restarted, but it wouldn't go very fast. Sounds like they seized the piston. No doubt about it, this machine has been hot. Well, let's get to the compression test.
Let me help with that.
Thanks. Only 95 psi. The service manual says that there should be at least 170 psi. So it definitely needs top end work.
But why did it seize?
See, the customer said that they rode this machine around here all summer long with no problem. So it sounds like the jetting was okay. Oh, but they did say that they had trouble getting it to idle down right. Do you have any ideas?
The idling problem may indicate an air leak, leaning out the fuel mixture and causing a seizure.
I'll check the intake tract and the fuel petcock and the carburetor. A clogged petcock or main jet could lean out the fuel mixture and cause the engine to seize. Well, I've cleaned and inspected the whole carb, the petcock, the intake manifold, and the rest of the intake tract, and nothing.
The next step is to check the timing and the ignition system. If an ignition component was faulty, the ignition timing could be advanced too far, causing a seizure. Also, advanced ignition timing can cause hard starting and a rough idle. Notice the oily film covering everything inside? That could be a clue to the cause of the seizure.
Well, the oil couldn't have come from the transmission, so it had to have come from the engine crankcase. Well, that means that the ignition side crankshaft seal must be leaking, allowing the fresh air fuel mixture to escape, creating a lean fuel mixture and eventual piston seizure. But we gotta be sure.
A crankcase pressure and vacuum test is the only way to pinpoint an air leak, so we'll use both pumps. By the way, on some CRs, the transmission is internally vented to the ignition case, so be careful not to misdiagnose the problem.
Now what?
Bolt the adapter in your left hand in place of the carburetor, blocking off the intake tract. Then attach the adapter in your right hand in place of the exhaust manifold gasket, blocking off the exhaust port. When those are sealed, we'll be ready to test crankcase pressure and vacuum. Rotate the crank so that the piston is at bottom dead center and pressurize the engine up to about 6 psi. The engine should lose no more than 1 pound of pressure in 1 minute. We know this engine has a big leak. The trick is to find it and fix it. After we find the problem, we'll have to retest the engine to see if there's more than one leak. That clinches it. After striking the seal with a chisel to loosen it, a cotter pin pulling tool may be used to remove all but the most stubborn crankcase seals. Slip the point of the tool under the seal lip. Then, using a small piece of wood as a fulcrum, pry out the seal. Now let's inspect the bearing for wear or damage. A worn bearing can cause seal failure. Next, clean the seal bore in the case. Dab a small amount of grease on the lips of the new seal, then carefully drive it into place.
We changed the seal. Does that do it?
Probably, but we'll have to retest the seal with our pressure tester, and we may have to check other areas for leaks as well.
Yeah, it looks good. But what if it had still leaked?
Then check the ignition side crankshaft seal with soapy water. Watch for bubbles. Okay, so the seal you replaced is good. Next, check the reed cage. Over-torquing these bolts can distort the cage and cause it to leak air. Then the cylinder base gasket. Next, the cylinder head gasket. Nothing suspicious here. And fifth, the gasket where the crankcase halves mate. This isn't too common, but it can happen.
Could there be leakage between the transmission and the crankcase?
If it leaks at the transmission or at the primary drive crankshaft seal, which is more likely, the engine will probably suck transmission oil into the crankcase and smoke excessively, besides fouling plugs. A good way to check this is to drain the transmission oil and replace it with castor bean oil. Bean oil gives off a very distinct aroma when it burns, but if you're checking a scooter, this doesn't help much. A scooter has no transmission oil.
So how do I tell a primary drive crankshaft seal failure from a leaking gasket at the transmission, since both symptoms are the same?
Since you can't see inside the case to inspect the gasket, first test the primary drive oil seal by pouring oil around it while the crankcase is pressurized. If you don't see any bubbles, the problem is the crankcase gasket. That checks the engine for pressure leaks, but since the engine must hold pressure and vacuum when the engine is running, let's connect this vacuum pump and apply 6 inches of vacuum. In 1 minute, the engine should lose no more than 1 inch of vacuum. It's held vacuum for at least 1 minute now, so the crankcase checks out okay.
Well, what about rebuilding the top end?
Look in the service manual when you've left the tech zone. It'll show you everything you need to know about rebuilding a Honda two-stroke engine. And don't forget to take a plug reading after rebuilding the engine to make sure the carburetor jetting is correct. But don't get excited. We still have one more two-stroke RO to complete. And we need to get to it.
Well, let's see, the customer complained of hard starting and four-stroking in the high RPM range.
Four-stroking. Oh, you mean firing every other stroke?
Yeah, and plug fouling. Hey, you're pretty good at moving things around. Where are you when I need to put a gold wing on the lift?
You were saying?
Yeah, well, it says here that the CR seems to run okay in the mid-range, but, see, the customer just moved from the low desert up to the mountains, so bike is new, probably hasn't been ridden more than 3 or 4 times. I bet that they didn't rejet the carb for the higher altitude and the colder air.
The carburetor jet selection chart in the owner's and service manuals show the jetting needed to make the machine run properly, given the difference in altitude and temperature.
So all I need to do is find out the higher altitude and the average air temperature for where the customer is riding now.
Right! Honda's come from the factory with the correct jetting for sea level, with an air temperature of 68 degrees Fahrenheit. We'll use the stock jet numbers for our base calculations, but first, let's make sure the carburetor is working properly. While you're doing that, record the present setting of the needle clip and the air screw position. Also, record the main and slow jet sizes. But before making any calculations, check the race support newsletter to see if the factory team has made any changes to the base setting. Any changes would affect our calculations for altitude or temperature. There are no changes recommended for this machine, so we'll go with the original base numbers. After checking the base settings, multiply the base carburetor jetting by the correction factor to determine the new carburetor jetting requirements.
On this customer's machine, the base jetting is the standard jetting from the factory. The area where he rides has an altitude of about 6,200 feet and an average air temperature of 70 degrees Fahrenheit. Correction factor is 0.94.
Now, multiply the base main jet size of 175 times 0.94.
It's 164.5.
Right. The closest jet size is a 165, so that's the one we need. Now let's see. 0.94 times 60, the old slow jet size.
It's 56.4.
So the closest jet size is 58. That's the new slow jet size.
So the customer needs a 165 main jet and a 58 slow jet. According to the manual, A minor adjustment to the air screw position is necessary. But the jet needle clip stays in the standard position. Well, it looks like the customer's settings were way too rich at both the high and low RPM.
Sounds right, but only a test ride and plug check will confirm the proper jet selection. And remember, to prevent engine damage, it's good practice to go one size richer on jets if there's any question about the right size. The premix ratio also affects jetting. Honda has determined that a ratio of 20 parts fuel to 1 part oil is the ideal mixture for maximum engine durability. And all of the jetting recommendations are formulated for the 20-to-1 premix ratio, which also happens to produce the best power.
Some of my racing buddies mix oil at much higher ratios, like 50-to-1. How does that affect jetting?
Using 50-to-1 means the engine will receive more fuel and less oil, similar to going one jet size richer in fuel but much leaner in oil. And that can cause engine damage from inadequate lubrication.
The jetting is right, the timing check's perfect, but the engine is still too hard to start. I could use a clue if you've got any.
Remember that the HPP system improves this engine's performance for the entire power band by varying the size and opening duration of the exhaust port. Even though Honda's HPP system has proven to be very reliable, it does need to be decarboned every 2.5 hours of operation. And given the overly rich running condition of this engine, it's possible that the HPP valves are carboned up. That could be the cause of hard starting. Again, the service manual will tell you how to decarbon HPP valves.
Boy, the HPP system works great now with the carbon removed.
George, now that you've conquered 3 tough two-stroke troubleshooting problems, let's quickly review what you've learned about Honda two-stroke engines. Remember that on the upstroke of the piston, a negative pressure or vacuum is created in the crankcase and intake port. As this happens, the reed valves open, allowing the fuel mixture to fill the crankcase. Just before the piston reaches top dead center, the spark plug fires, igniting the fuel mixture, forcing the piston down. The piston pressurizes the crankcase, closing the reed valves and compressing the fuel mixture. As the piston continues its downward stroke, the exhaust and transfer ports are uncovered. The pressurized fuel mixture in the crankcase enters the combustion chamber through the transfer ports, forcing the spent gases out the exhaust port. Then the piston begins its trip upward again, forcing the remainder of the exhaust gases out, closing off the transfer and exhaust ports, and finally compressing the fuel mixture before the spark plug fires.
Well, I'm with you so far.
What does this graph tell you about scooter troubleshooting diagnosis?
Using this chart, after test riding a scooter with the tachometer, will tell you if a poorly performing scooter has engine or drivetrain problems. If the RPM of the scooter is too high in relation to road speed, the drive unit is probably slipping. If the RPM upper limit is too low, the engine probably needs adjustment or repair. It's always a good idea to check the service bulletins and the wrench about the models you're working on before beginning any work.
Also remember that the January issue of the Wrench includes a listing of all the previous year's articles by subject and the previous year's service bulletins by displacement. Remember that a crankcase pressure leak can occur in 6 locations. They are
the ignition side crankshaft seal, the reed cage, the primary drive side crankshaft seal, the cylinder base gasket, the crankcase gasket, and the head gasket.
Now, with the help of the service manual, let's see if you can compute the jetting change needed for a 3,000-foot increase in altitude and a decrease of 20 degrees Fahrenheit temperature, beginning with a 160 main jet and a 50 slow jet.
Okay, just give me a minute.
Gotta go. See you around, George.
If you're about done with those 2 strokes, I've got that 4-stroke RO you wanted.
I've got some more top-end work to do on this TRX, but I'll be happy to work on another 2-stroke. They're a piece of cake, once you understand how they work.
Submitted for your approval The case of one George Smith, a technician who's now in tune with his work.